Now let us see how problems are solved using finite element analysis. This video is intended to introduce some of the basic terms in finite element analysis. Let us consider the example of a plate where three sides are at temperatures T1 and the fourth side is at temperature T2. The problem here is to find the temperature T at any location. In finite element analysis, we divide this domain into a number of elements. This is known as discretization or meshing. Now let us take one element from this. We have used rectangular elements to discretize the domain. I'm showing a single element separately. We are familiar with differential elements of size, say dx, dy. We have used these to derive equilibrium equations for elastic problems or heat conduction equation, etc. Now, this element that I've drawn is not a differential element, but this is a finite sized element, or simply a finite element. The vertices of the element are numbered, and these are known as nodes. In finite element analysis, the equations are formulated such that the values of the field variable, here the field variable is T, the temperature, are computed at the nodes. Which means for a particular element, we will compute the values T1, T2, T3 and T4, which are the values of temperature at the nodes. Let me repeat. For the problem, we write equations such that the values of temperatures are only computed at the nodes. Now, how do we find the temperature inside an element? Say this point, T. We use the values of T1, T2, T3 and T4 to calculate the value of the temperature at an inside point in the element. We can calculate T as T is equal to N1 T1 plus N2 T2 plus N3 T3 plus N4 T4, where N1, N2, N3 and N4 are known as interpolation functions or shape functions or basis functions. We will use the term shape functions in this course. We will later see how to select these shape functions. This element is said to have 4 degrees of freedom because 4 nodal temperature values T1, T2, T3 and T4 are required to express the temperature T at any point inside an element. If our problem was a plate which is loaded in 2 directions and fixed at 2 edges, let us see how many degrees of freedom this element would have. If you consider this node 1 alone, and since this plate is loaded in both x and y directions, the point 1 will move something like this to a new point, say 1 dash. I've drawn it a little bit bigger on the right side, the element. For this problem, the field variable is the displacement u. And if you see, this displacement u has 2 components, the x component ux and the y component which is uy. Therefore, to describe the displacement at any node, 2 components or 2 numbers are required to represent the displacement. So at the node 1, ux1 and uy1, at the node 2, ux2 and uy2, node 3, ux3 and uy3, and node 4, ux4 and uy4. Therefore, 8 nodal displacements are required for this element. Therefore, we can say this element has 8 degrees of freedom and this element has 4 degrees of freedom. We will discuss the types of elements later. So far, we have seen that for solving a problem using finite element analysis, we have to first discretize the domain. We have to then formulate equations to calculate the value of the field variables, here it is temperature, at the nodes. To find the temperature within an element, we use nodal values of temperature and shape functions. We have also seen that the degree of freedom for the element we considered is 4. The next step is to formulate equations for every element. Here we have divided the domain into 9 elements. These equations for every element are then combined or assembled, considering the connectivity of the nodes. To explain connectivity, let us take this element, let us name it as 1, and this element, let us name it as the 5th element. I have drawn these two elements side by side separately. Let me number the nodes of these two elements. If you see these elements 1 and 5, we know that this node is shared between these two, or the node 3 of element 1 and node 1 of element 5 are shared. Suppose I note the temperature at the node 3 here as T3 of element 1 and this temperature as T1 of element 5. We know that these two temperatures, being the same shared node, should be the same. So the equations of individual elements are combined or assembled, considering that the shared node would have the same temperature. That is what we mean by the connectivity of the nodes. Now, the assembled global finite element equation is solved applying the boundary conditions. The purpose of this video was to introduce you to some of the terms in finite element analysis. Terms like element, finite element, node, shape functions, degree of freedom, and I've also tried to outline the procedure used in finite element analysis. Next, we will take the case of a one-dimensional axial loading problem and formulate the equations and solve it.